Hello, hello, hello. I wanted to make a quick video. It's kind of an interesting thing came to my mind, and I'm not really sure what happened. uh, here's the puzzle here. I kind of came up with an infinite, I guess, square root expansion to represent I, the square root of -1. And so I started and I said, well, I, by definition, is the square root of -1. But we know by Euler that e to the I theta is cosine theta plus I times the sine of theta. And so if you let theta equal pi, then you get that e to the I pi is -1. So then I said, well, I could make this the square root of e to the pi I, since by Euler, e to the pi I is -1. And then I said, well, look at this. This is a recursive definition for I, because we have I being equal to something with I in itself. So I could replace the I with the whole thing. So in other words, I could make it e to the... So I need to make maybe a bigger square root. Maybe not that big. In the middle. There we go. E to the pi square root square root of e to the pi I, like that. I replace the I with this here, but then I could do it again, right? I'm gonna need a bigger square root, so maybe something like that. I can make it e to the pi times the square root of e to the pi square root of e to the pi I. Would go there. Yeah, I think that's all the parentheses. But then I could do it again, right? And so if I were to do it ad infinitum, ad nauseum, I would get that I is a big square root e to the pi square root e to the pi square root e to the pi square root, and then I have so on and so on, and I have all those square roots nested inside of each other like that, and then I would have a bunch of parentheses I would close off there. But so at first you'd be like, cool, I guess. But here's my problem with this recursive definition of I. Well, for one, if we were to cut this sequence off at any particular point, in other words, maybe here we were to apply this recursive definition of I one more time, and so we'd have e to the pi square root e to the pi square root e to the pi square root of e to the pi I, and then we just stop right there. And we wouldn't keep going forever like how we did here. Then that sequence is, well, for one, it's monotonically increasing. So it doesn't converge to any specific bound. And even more problematic is that it's, no, I'm sorry, never mind. Ignore that part. This one here is monotonically increasing, right? If I just keep doing e to the pi square root, if I have big square root, e to the pi square root, e to the pi square root, e to the pi square root, that is, for one, monotonically increasing. However many times I do e to the pi square roots, it's just going to get bigger and bigger and bigger, because e and pi are real numbers greater than 1. And second of all, it's there's no imaginary part at all in there, right? This is real, this is real, this is real, real. And so it just goes on forever and ever and ever. Now, I guess, like, let's say they just gave you, let me erase this here. I don't know, maybe if you had a problem and they just gave you this here. Oop, And let me get rid of that. If they just gave you this here, and they said, what is this? I don't even know if the word would be converge, because obviously, I mean, just looking at it, it doesn't converge. I guess what number or something or constant could be represented by it, then, I mean, the traditional way to go about it is to say, all right, well, this thing is going to be equal to y, and if this whole thing is equal to y, then, see if I can get my laser, then this whole thing is also equal to y, because the nested roots are infinite, so we can get that y is equal to square root e to the pi y, and so y squared is e to the pi y. E to the pi y, that sounds like it could be like a rap sound. E to the pi y. E to the I to the E. Wait, e to the I to the E I O. Anyway, and so I guess just looking at this, I'm not sure how you would actually determine this algebraically, but by inspection, I mean, you could look at this and you could go, all right, well, y is equal to, would negative I also work? I know y equals I would work, because negative 1 is indeed e to the pi I, and e to the negative pi I, well, let's see. If I plug in negative pi, cosine of negative pi is cosine of pi, which is negative 1, and yeah, so that's interesting, right? Because y equals I works, negative I works, but also this equation here has a real result as well. Like, if I were to graph it, well, we have y squared, and that's just a parabola, and it's, do my best to accurately graph it here. So y squared is going something, wow, I had the thing on, oops. So it's going something like that. And then e to the pi y, that's going, it's low here, and then it goes up, and well, it actually doesn't intersect there. It goes up, and it won't ever cross at this particular point here, but it does. It necessarily has to have an intersection point on the left side of this parabola, and there is no explicit way to get that solution. You could maybe approximate it with the Taylor series, e to the y being sigma n equals 0 to infinity of, what is it? Oh, x to the n over n factorial. Yeah. Okay. But, so my questions, because I don't know the answers. My questions are, well, first of all, this here, it doesn't even look like it converges to anything like nice at all. Like, it's monotonically increasing, at least in my mind. So why it would converge to, oh, and by the way, the root here, according to Wolfram Alpha and Desmos, that point there where they intersect is approximately negative 0.475, comma 0.225. So why does this converge, at least for the real numbers, to, I mean, a real number at all? It doesn't even look like it will converge, but it converges to a negative, or, well, it does, it converges to a positive real number, never mind. But, I mean, a decimal of all things, it seems totally odd. That's my question, is why does this converge to that, that real number there? It just seems strange to me. And then my second question is, For the imaginary roots, why is it y equals plus or minus I? I only made this based on the definition of I being, this is the positive version of I. Negative I is negative square root of negative 1. Maybe it's because of the fact that whether I plug in pi or not, this is going to give me a 0, whether I plug in pi or negative pi. And this is even, so whether I plug in a pi or negative pi, it's going to give me the same answer. But yeah, these are my questions. Tell me what you